I think we have two great presentations today. I've really been looking forward to this. So we're going to be starting off with Alex Ropelewski from Pittsburgh Supercomputing Center, and he'll be talking about his experiences working with 2 Campus Champion Fellows. And then at the bottom of the hour, Justin Matejka, I hope I got last name pronounced correctly, from Autodesk Research is going to be presenting about exploration and visualization of large data sets. So, we'll have about 5 minutes at the end of each talk for questions. If you have a headset, please use that if possible. It improves the audio quality. For January and February, we already have speakers booked, but we still have a lot of openings for most of 2019. From March onward, we have 16 slots available. So for all the fellows, the fellows, the ECSS staff, if you are interested in presenting at the ECSS Symposium, we would really appreciate that. So just get in touch with me. Hold on, let me just check the chat. Oh, so okay. So with that, it's now 3 minutes past the hour. I will turn things over to Alex. So Alex, go ahead.
Hi, thank you. So today I'm going to spend some time talking about my experience working with 2 Campus Champion Fellows on bioinformatics projects. Both of the projects, I'll give you a little introduction to those, talk a little bit about how the Campus Champion Fellow contributed to the project, and then finally I will conclude by giving giving the entire ECSS community some advice on what I think works well when you're working with a Campus Champion Fellow on a project, in case anyone has the opportunity to do so in the future. That said, I will skip to the bottom line and say that it has been very rewarding working with Campus Champion Fellows, and I would highly encourage anyone from ECSS, if the opportunity presents itself to you, to by all means take advantage of that opportunity. And my slide is not advancing. One more second here. There we go. All right. Hopefully I didn't click the button too many times so it goes forward. But for those of you, many of you in ECSS know who I am. For those of you who don't, let me give you a brief background. I am the Director of Biomedical Applications at the PSC. I've been involved with high performance computing and applying high performance computing with 2 biomedical problems for virtually my entire career. Most of my career has been spent working on NIH-funded projects. However, I have been a part of XSEDE since about 2012 to provide bioinformatics support to communities. I'm on a number of NIH-funded projects. I'm PI on a few of those. One of those projects, the Brain Image Library project, which Derek gave an outstanding presentation on earlier this year. I've also been involved a lot with training, particularly bioinformatics training. We, at the Pittsburgh Supercomputing Center, ran a MARC program focused on establishing bioinformatics at minority-serving institutions. Also involved in training on a modeling project, on a multi-scale modeling project as well. I've also, in addition to NIH-funded projects, I've also worked on some other projects that are bioinformatics related that I wanted to point out. These projects principally involved cancer data for both the Pennsylvania Department of Health, a funded project, and for a project funded by the Aurora Foundation. And for those of you who are interested on what the the animated GIF is on the bottom left of the screen, that's actually going through a mouse brain. It's one of the data sets that's included as a part of the brain image library. So for those of you who are not familiar with the Campus Champion Fellow program, it is a competitive program that's open to all XSEDE Campus Champions. Generally speaking, about 4 Campus Champion Fellows are selected each year, and it is a 1-year program, and there is some limited support for both travel and release time support for the Campus Champion as well. And really the goal of the program is to increase expertise on campuses by including campus champions on ECSS projects. So instead of having the typical ECS project where there's ECS staff members and the PI's research team working on a project, the campus champion is also added in that mix as well. It is kind of unique in the sense that the campus champion who's selected selects the ECS project of interest. However, there is some coordination with both the PI and ECSS staff, and if either one feels that the campus champion who wants to work on the project is not appropriate for the project, either can decline. So as I mentioned earlier, I had the opportunity to work with 2 Campus Champion Fellows. The first Campus Champion Fellow that I've worked with is Brian Cougar, and I worked with him in 2014. Brian is very well versed and was very well versed in bioinformatics, as well as high performance computing. One of the things that Brian did early on prior to the fellowship program is he did produce one of the largest, and at the time it may have been the largest, assembly of soil microbial community on our system at the PSC, which was Blacklight at the time. Brian has been successful after the fellow program. He's currently XSEDE domain champion for bioinformatics, and he has been hired and works at Oklahoma State's High Performance Computing Center. So the project that Brian helped with was a project involving cancer genomics from the University of Pittsburgh, led by Uma Chandran. And the goals of this project, the principal goal was really to mine cancer sequence data to discover unique features such as gene splicing events or unique polymorphisms that are identified or could be identified in certain populations or subpopulations of folks that had cancer. The data sets that we were working with, there was 2 different types of data that at the time Uma's lab was working with. One was exome sequencing data from a sequencing platform called Solid, which is no longer manufactured, as well as RNA-seq data from the Illumina platform, which Illumina is still in business. And most of the sequence data that we get today, particularly on the NIH side, is Illumina data. The scope of the project was really to develop the workflows, and that involved both identifying the best programs out there for working with the data types that we were working with, as well as installing the codes on the machine and linking everything together in a way that the PI would find useful. Some of the results from the project, the PI has continued to use XSEDE resources to this day, and the PI and myself have worked on some other independently funded projects as well that are cancer related. So Brian's real contribution to the project, actually he had many different contributions to the project. He was a joy to work with. He really took the lead on the RNA-seq workflow that the PI wanted to put in place. Brian gave a lot of advice on what should be included in that workflow, put together a sample workflow, ran that sample workflow with the PI's data, and helped the PI interpret the results of that workflow. The PI, Uma, was very pleased with Brian, and they did discover several interesting results that Uma was going to pursue further. And as I mentioned earlier, this success, Brian has built on this success, and he is the XSEDE domain champion for bioinformatics. The second Campus Champion Fellow that I've had the opportunity to work with came from Southern Illinois University. And Chet, there at Southern, I mean, I guess probably most of you have never heard of Southern Illinois University. Southern Illinois University is a small university in Southern Illinois. And as a part of that, Chet provides support to research projects there. His background is computer science, and Chet is essentially the only person on campus providing support, computational support for research projects. The project that Chet chose to work on was the project that I have with Ping Zhou and Hugh Lee at Tennessee State University in Nashville. And that project is on the de novo assembly and annotation of goat, rumen, bacterial, and fungal metagenomes. So the goals of the project are really to identify the populations in the goat rumen microenvironment, to identify functional genes that have potential either biotechnological or pharmaceutical potential, as well as potentially recovering novel draft genomes from the metagenomic data sets. So the scope of the project really involved developing appropriate workflows for this data to enable using metagenomic tools through the Galaxy interface on bridges, as well as to assemble and annotate the data. So with this project, there were some surprising results. One of the surprising results was the data set that we had thought was a fungal data set. Once we started doing the analysis, we've identified that data set was probably bacterial in origin rather than fungal in origin, because there were very few hits with fungal sequences in that data. And we did feature this work as a poster in the PERC 18 conference as well. Just a little bit more information on the project itself. This is a supercomputing level project. The assembly itself ran on the 3 terabyte nodes at the PSC. Annotation also ran on the larger memory 3 terabyte nodes as well. And when we looked at the bacterial data, there essentially weren't a whole lot of surprises in the sense that what we had found when we did a phylogenetic classification were mostly what we had expected to find. But obviously the devil's in the details, and just because something is classified as one category or another doesn't mean that it's not necessarily a novel bacteria that people haven't discovered. Bacteria tend to change quite a bit and have unique properties because of this ability to change. We're also currently, where this project stands, is we're currently submitting the data to the public databases. And I do want to mention that this is a significant issue that I've run into with bioinformatics projects in general, particularly with folks who are doing bioinformatics projects at non-major research-intensive universities. A lot of times, this is the first time that the researcher has to submit data to a public repository. The nomenclature is very confusing for them. And a lot of times I end up helping the researcher to go through the process. So the impact of the project has been great. I've got a quote from Hui on this slide here. This is really one of the first large scale metagenomic projects that has been undertaken at Tennessee State University. For those of you who aren't aware, Tennessee State University is a historically Black college, and it has a strong agriculture department, and that's where Hui and Ping reside. Chet, I think, also learned a lot about this project as well. Some of the key contributions that he made to the project were really to take over the fungal metagenome assembly and try to get the codes in order, the pipelines worked out to analyze that data. And as I mentioned earlier, that we thought that the data was fungal and it ended up being bacterial. Chet is the one who discovered that. Whenever we were trying to analyze the results, he showed us the results, and we took a look at them and said that, well, something's not right here. So we had to do some additional analysis to convince ourselves that it was an issue with the data itself rather than some of the computational methods that we were using at the time. So in that sense, Chet really contributed a lot to the project. In other sense, I think that science is messy, and I don't think that Chet had expected science to be so messy. But nevertheless, the impact on Chet has been positive. He learned how to use a whole lot of tools, a lot of bioinformatics tools that he otherwise would not have been able to be exposed to. So those are the two projects and the two campus champions that I've worked with. Now I'd like to take the remainder of my time and describe for you some of the lessons that I've learned from these projects and some advice that I have to give to others who may have campus champions working with them in the future. The first thing, and this goes for bioinformatics in general, is that it's very important to assess the skills of the team. And by the team, I mean the whole team, including the PI, the people working for the PI, as well as the champion. A model that I like to use, and I find very useful for illustrating this point that every bioinformatician is not equivalent, is taken from an article published in the PLOS One journal. And in this particular article, the reference is at the bottom of the screen, if you want to look it up. They categorize 3 different bioinformatics user personas. They categorize these three personas as either a bioinformatics user, a bioinformatics scientist, or a bioinformatics engineer. Conceptually, you can think of a bioinformatics user as a biologist who's learned how to use a few bioinformatics tools. On the other hand, a bioinformatics engineer is a computer scientist who does a lot of programming, but the programming that he does is more bioinformatics oriented. And then in the middle is the bioinformatics scientists themselves, who's comfortable with either domain. I would say that each group struggles in some way. The bioinformatics users struggle to use the command line, and the bioinformatics engineers struggle to understand the biology, particularly the biological nomenclature that tends to be used in projects as well. So it's really important that from an ECSS perspective, when you're working on these type of projects, that you understand who is working on the project and what their viewpoint of bioinformatics is, and that way you can help better match and provide better mentoring to the individual. Some additional items that I think are important. The first is to introduce yourself to the fellow as soon as you can. Typically, this is done at the PERC conference, and I would highly recommend that if you're selected to have a Campus Champion Fellow work on a project with you, even if you were not planning on attending the PERC conference, it's probably a good idea to show up and meet the Campus Champion Fellow, even if you can't stay for the whole conference. It's also important, I think, to define a successful outcome up front. It's important to ask the fellow, what do they want to get out of the experience? It may not necessarily be the same as what the PI wants to get out of the experience, or you want the fellow to get out of the experience. So it's important to understand what their needs are and what they consider to be a successful outcome. And it goes without saying that some projects are more ideal for the interactions with Campus Champion Fellows than other projects, both in terms of interest as well as in the requisite skills that are needed to get started on the project. It's also important to integrate the fellow into regular meetings that you have with the PI's team. And I'm a firm believer in face-to-face meetings. Now, unfortunately, there's not enough money in the Campus Champion Fellow budget to have more than one meeting, but it is important to have that face-to-face meeting with the ECSS member, the Campus Champion Fellow, and the PI's team. And I think it's also important to manage expectations in the sense that research is messy. And this is both on the PI's front as well as the fellows front. The PI may think that the Campus Champion Fellow can do certain things that the fellow is not able to do, and vice versa. And I guess the other real thing to consider is that most research projects are multi-year project, and the fellow is only going to be around working on the project typically for 1 year. So the fellow's role on the project needs to be discrete and defined well. And finally, speaking of outcomes, I do want to get on my soapbox and preach to the ECSS community in the sense that we really need to be concerned with outcomes in the forms of grants, patents, peer-reviewed publications, and data sets and software. This is really how the outside world judges us as scientists. And I think a lot of times we have these nice play toys called high performance computers, and we really get into coding and making things work really well. But we don't always follow up with the publication that describes what we've done, why it's important, and get the recognition that we need for that project. Now, that said, I think that if you expect to have a peer-reviewed publication, a one-year time frame in general is unrealistic for such a great outcome. And I just throw up this one example here on the PERC conference, which a lot of us have published at. Papers are due literally 6 to 9 months after the Campus Champion Fellow had started working on the project. And just to bring this point home once again, this is a diagram of some of the projects, some of the bioinformatic projects that I've worked on that show when the project started, when there was enough results that people were comfortable with to either give an oral or a poster presentation at a conference, when things were final enough to actually submit a paper and get it published, as well as deposit the data in the database. You'll notice that many of these are not in that one-year time period. And again, to kind of beat on the publication, I always make it a habit to put language like what's on my screen here in my ECSS work plans, in the sense that if I'm contributing intellectual to the property and that work gets published, then I should be a co-author on that paper. Likewise, if I'm using the data that was produced from the project and made some modifications and had more of a computation-oriented paper, that I should give authorship as well to the contributing group members from the PI's group. And finally, I just want to say that working with Campus Champion Fellows is a great experience, particularly for those who like mentoring. And I encourage everyone to give it a try. Thank you. Any questions?
Great, thank you so much, Alex. We have time for a few questions. Just remember to unmute first.
Hi, Alex. This is Mona. I have a question. Thank you for that presentation. I was wondering, is a publication required when you have, as a result, when you have a campus champion on your project?
A publication is not required, but I think that we let a lot of opportunities go away. If we have as a goal that that's one of the things we want to do, it's more likely that that's going to happen than if we don't have that as one of our goals. But no, it's not a required goal of the program.
Okay, and another question is, can a project request a champion, or is it that they get a list and they choose and there's nothing we as ECSS staff can do?
I'm not sure how to answer that question because I'm not as familiar with some of the others on the line, perhaps with the Campus Champion program. I know that whenever it's gotten to the point where a Campus Champion has been selected, I've been asked whether or not this is something that I think would be appropriate. I don't recall volunteering projects for potential Campus Champion Fellow uses, but I may not be remembering things correctly.
Yeah, so Mona, this is Bob. I'll just chime in real quick. I'm not aware of any way for an ECSS PI to request that there be a Campus Champion Fellow work on their project. We could look into that, but I think it's really more appropriate for the ECSS staff to determine whether or not it would be appropriate for a Campus Champion Fellow and whether they're willing to take on mentoring of a fellow.
Okay, thank you.
All right, do we have any other questions? If not, let me just make a quick comment. Again, Alex, thank you for that great presentation, and we really appreciate your serving as a Champion Fellow twice. So again, thank you very much.
Thank you.
So we will switch over to Justin, if you want to go ahead and share your screen.
Okay. Is that working?
Yep, looks good.
Okay. Well, thanks for having me. So I guess I'll give a little bit of background information here first. So I am from Autodesk, and for those who don't know, Autodesk is a leader in 2D and 3D design and engineering and entertainment software. So a software company with about 10,000 employees, most known for AutoCAD, but we have many more products beyond that, both for sort of industrial design type work as well as media and entertainment products for movies and the like. And in particular, I'm part of Autodesk Research, which is part of the office of the CTO here at Autodesk. And so this is sort of the research wing of Autodesk, the industrial research lab within the company here. And so within Autodesk Research, which is made up of, I guess, around 70 researchers, research scientists, developers, we're doing research in a sort of wide range of topics. And in particular, I'm part of the user interface research group. So in this group, we focus on problems relating to human-computer interaction. And so within this group, we work on publications and publish them at sort of the top tier ACM conferences of CHI and WIST mostly. And the work I'm going to present today was actually published at CHI, which is where Mona saw the presentation and reached out and thought it would be of interest to this group. So thanks both to Mona and Bob for inviting me here today. And so I guess within human-computer interaction, within HCI, I mostly focus on data visualization, particularly figuring out ways to take large, complicated data sets and let people make better sense of them. And so, back to this project in particular, it's called DreamLens, and it's the exploration and visualization of large-scale generative design data sets. And so generative design data sets is sort of the key thing here, which I want to talk about briefly. So say you've got a monitor. This is just an example situation here. Say you've got a monitor and you want to make a stand to raise it off the surface of the desk. If you were using traditional design, you would design the stand directly. So you'd have this problem. I want my monitor raised up, and you would design the solution directly. But with generative design, things are a little backwards. Instead, you design the problem and have the computer generate a solution. So for example, you could say, I want my monitor stand to have 3 pads on the desk like this. There should be a top surface like this. And then once you've defined the problem, the computer can go off and generate a solution. And so here we're using a topology optimization tool developed in another part of Autodesk Research called Project Dreamcatcher. And so, I think that creating a single solution to a design problem like this is actually really cool and amazing on its own. But to me, even more exciting is the possibility of creating hundreds or even thousands of design variations, which all satisfy the design criteria. But then, as the designer, you're left with this task of finding which design or which designs are the best, right? Which one you're actually going to move forward with and manufacture. This sort of design is sometimes called divergent generative design, rather than convergent generative design, where only a single output is created. Here, we're trying to create a wide variety of outputs, and then we have to pick which one we want to go with. However, this notion of what's the best design, which design should we move forward with, is it's hard to figure out. The answer of what is best can be quite varied. so far we're seeing a lot of generative design in what I would call really sort of engineering-y scenarios. So for example, this is a partition made by my colleagues at Autodesk in collaboration with Airbus, which is 50% lighter than the old style partition that was used in these planes and saves over 12,000 kilograms of fuel per plane per year. But this structure is hidden behind a wall within the airplane, so nobody's ever going to see it. So properties such as weight and strength are important, but aesthetics are not. It doesn't matter at all what this looks like because no one's ever going to see it. On the other hand, we have things like this. So this is a beautiful mug designed by Nervous System. And with this, the designers created a bunch of generatively designed variations and had to pick which one they wanted to manufacture. Although here the choice is primarily, if not entirely, an aesthetic choice. The physical properties of each of these designs are basically the same, and they don't meaningfully change between variations. So if we look at sort of the ways we can see generative design being used in this sort of physical design sense, it really are these two camps. The really engineering focused, just give me the strongest, lightest thing possible. And on the other side, we've got sort of the artist types who are using generative design, for its creative and aesthetic possibilities. But I think there's really a great deal of promise for generative design in the middle, solving problems that have both an engineering and an aesthetic component to them. And so that's what we're trying to look at with this project. And so, to explore this space of generative design in the middle of engineering and art, first we need a data set. So to do this, we set up this monitor stand problem that I mentioned before. Of course, so we're trying to raise this monitor stand up. And of course, it's not a particularly hard problem to solve. My frugal colleagues like to point out that you could just use a shoebox, but say you want to make something more designerly than that. And part of the reason with creating this design task in particular is that it's a design task that anyone could appreciate without knowing the specifics of some airplane component. So here's the setup for this monitor stand. We've got these fixed feet, which will be placed on the desk, and these platforms that'll hold the monitor, and then loads, so middle loads and end loads, which can vary to change the resulting stands that are developed. So yeah, to create these variations, because if you just set up the problem one way, you're always going to get the same result. So we wanted variations. To create these variations, we used 5 different values for the middle load case and 5 different values for the edge load cases between 100 newtons and 2000 newtons. And then looking at the sort of parameters of the solver, we used 3 different voxel sizes and 3 mu values, and mu is an internal setting for the topology optimizer. And then each solution is run for 74 iterations, as this topology optimization process is an iterative process where each iteration also results in a valid design. And so this results in over 16,000 total designs. Generation process isn't particularly fast, so it takes about 3 minutes each for design. And then so this results in about 36 days of GPU time to generate our data set here, which we were able to parallelize over a number of GPUs, so we could do it over a 4-day weekend. And so by doing that, we get our 16,000 designs. However, the incremental change from one iteration to the next iteration can be quite small. So to try and cut down on the number of very similar designs, we did some pre-filtering of the full data set by only keeping designs from a subset of iterations. So we kept 20, 30, 40, 50, 60, and the final iteration. And beyond that, we removed designs which had parameters way outside of the standard parameters. And so after doing that, we're left with about 1,200 designs in this so-called filtered data set. And even at this small size of thumbnails, you can probably see that there's a good amount of variation in the resulting designs. So we have some very skinny monitor stands and some heavy ones, and then a whole bunch in between. So this is really where where this project starts, is now we've got this large, diverse set of design alternatives. How are we going to sort through them, or allow the user designer to sort through them? And so a few years ago at the WISC conference, we published another system called Video Lens, where the idea here was given a whole bunch of videos with a whole bunch of metadata about the events in those videos. How could you use that metadata to find relevant video clips? And so in this case, we happen to use baseball videos, since baseball has this sort of rich history of, well, a video of both of metadata and stats. And so, try as I might to get Autodesk to bring Autodesk Baseball Watcher to market, it just wasn't going to happen. But we were able to take what we learned about working with complex high-dimensional data sets and applying them to this problem of generative design. And so doing that led to this, which is what we call Dream Lens. And in setting up this sort of design problem, we had two high-level design goals in mind when putting together this system. The first was to highlight and emphasize both the physical appearance of the designs as well as their physical properties. So we want this tool to cater to both the engineer types and the artist types and everyone in between. And to do that, we have to be able to both cover appearance and physical properties. And the second is we want to encourage exploration of the data set. We have a potentially very large number of candidate designs, and maybe some that the designer themselves never would have thought of. And so we want the interface to support them thoroughly exploring this design space if that's something they want to do. And so looking back at the interface, you can see it's sort of nearly split in half. On the left-hand side, we have for the design viewer, so that's the area for looking at the actual geometry of the designs. And over on the right, we have a collection of tools for viewing, filtering, and selecting based off the model parameters. And parameters are split into two categories. We have the input parameters, which are the parameters which get fed into the system to create the designs. And model characteristics, which are the calculated properties of the resulting design, such as weight, strength, overhang percentage, that sort of thing. And so if we zoom in a little bit on these controls, we can get a better look at how they work. So we call each of these little strips a single attribute controller. And one of the principles of this interface is that whenever you see a dot, that represents a single design. So if we have 1,200 designs, that means we have 1,200 dots in each of these little strips, each representing a single design. So we have 1,200 designs, there's 1,200 dots in this weight controller. And so as the cursor moves over one controller, all the corresponding points are lighting up in all the other controllers to expose correlations between the various parameters. Over in the top, we have what we call the multi-attribute grid. This is where you can drag and drop different parameters up to the X and Y axes, as well as color and size controllers to plot multiple attributes together to more directly see correlation between different variables. And then also in this 2D scatterplot view, you could make freeform selection shapes to filter down the set of candidate designs. So, the overall design of the system is sort of designed to be extremely responsive, sort of really hyperactive, brushing and linking on all selections. So when you make a selection, it's immediately reflected in all of the other components. And so what we can see here is a user filtering down the set of designs using the controllers on the right, and then we can see the resulting candidate designs being displayed on the left. So besides working directly with the input and output parameters, we wanted a way to have designers actually work sort of at a higher level rather than controlling the weight or strength directly. And so the first way we do this is ranking by example. And so when we talk to people using generative design systems like this, or other ways of generating really large collection of examples, when people see a large set of designs, they really want to rank them. But typically they aren't really sure how, or they aren't sure what criteria should be used for the ranking. to address this, we created a ranking by example control. So rather than explicitly choosing which parameters are important and what values they should have, the user just finds examples they like and dislike, and then drops them onto this little widget down here. And then all the designs are ranked based on how similar they are to the liked designs and how dissimilar they are from the disliked ones. But then there's going to be weights of the individual parameters set automatically. You know, so if everything you liked was very similar in weight, then weight would have a high importance ranking. But then those can be tweaked manually if if the user decides that no, volume is not important. I'm going to drag that slider down to limit the impact of volume on my similarity calculation. And so the other sort of high-level feature we have in here is referred to as model stacking. And this came out of trying to think how we could let people interact with the actual geometry of the designs rather than their properties. And so, how can we enable, direct interaction with these, with the geometry? So what we see here is the set of active models being filtered down and the thumbnails for each model getting larger. But once we have less than 100 models left, we're going to see that there's no longer going to be static images. We'll have dynamic 3D rendered views. So now these are 3D views which can all be manipulated in unison to view the designs from the same viewpoint. But further, we can then stack all of these models into a shared 3D viewport and view them all in the same space. And the real key here is that in this stacked view, it's not a point cloud. We want to see the edges of each model. And so the way this works is by rendering each model independently in its own viewport and then compositing the viewports with alpha blending. As it turns out, if you set the bottom viewport to have an opacity of 1 and the one above it to be 1/2 and then 1/3 and 1/4, etc., you get the effect of each model contributing to the final overall view equally. And so here we can see the effect of stacking 4 similar designs versus 4 dissimilar ones, or stacking 100 similar and 100 dissimilar ones. And so this technique gives you a sense of the overall shapes of the set of designs and also areas of the space where there's high agreement or high variation. And so besides being able to view this collection of models in the stacked view, we also wanted to enable interacting with this stack directly. And to do that, we had a set of 3 tools: Chisel, Select, and Edge. So with the Chisel tool, the user clicks on the model sort of as if it were a block of marble, say, and we remove all models underneath the cursor. So it's kind of like whittling down a stack of models to a shape that they like. The second tool is called the Select tool, which is kind of like the opposite of chiseling. In this case, we only keep models which are under the cursor. So you would click to specify where you want the model to be, and all models which don't exist in that position are removed. And finally, we've got the Edge tool, which allows the user to draw a curve they'd like their design to have, and the system selects only those designs which match that curve profile. And so there's other features that we won't go into detail on, and in fairness, there is a lot going on in this interface. We're trying to present the user or designer with with a lot of information, with a lot of designs. And so we wanted to test this to make sure it's at least usable by our target audience. And so to do this, we ran 2 evaluations. The first was a lab study with skilled computer users to see if people could complete specific tasks with the interface, and in general they could. And the second thing we did was we ran a series of 17 one-hour-long feedback sessions with professional designers to get their thoughts on the tool and what they thought it could do for them. And at least for me, the most interesting comments from this group were about how the tool and process was exposing them to new ideas. And so if you've been looking closely at any of these models, you might have noticed some, maybe somewhat questionable outcomes. For example, this one. And so I initially thought there was a problem with the solver, and I went and talked with the topology optimization guys, and they said, actually, well, the solver is not set up to consider gravity. at the moment. So of course this would fall over. But it's a valid design if you were to think of it being bolted down to the desk. And I was considering removing all these because it sort of seemed like it was broken, but after leaving them in, this is the sort of thing that got the designers most excited. So for example, we had one participant say, these designs might not work, but it opens my mind. As a designer, I love these kind of things. So even if he wasn't going to use this design directly, he might incorporate this kind of feature into a stand he was making himself. And so if you look through, there's a whole bunch of designs that are, not exactly what maybe a human designer would have come up with, but finding these sorts of designs, really did get our users excited, and sort of led to the most extreme code I've ever received running one of these, where this person said you could find a whole new way of thinking about a problem. Before I'd have to go to the mountaintop to find inspiration. Now I can use Dreamlens. So we're quite happy with how the system has been received, and we think these sorts of ideas will be useful as generative design becomes more common. That said, I think the next big step for this type of work is have this process be tightly coupled with the generation engine. We want to allow the user to be able to guide the generation process rather than waiting for the process to finish. It's not practical to wait 36 days or 4 days even for the design variations to be created before going off and exploring them, especially if there's whole areas of the design space which the designer doesn't think are interesting. So we want the designer to be able to guide this process, as it moves along, which will save both computing resources, and we can, use those cycles for designs that, have a higher chance of being the successful one. And that's it. So, thanks again for having me. I'd be happy to take any questions.
Great. Thank you, Justin. Do we have any questions?
Yeah, Justin, this is Mona. Thanks for that. Also, another interesting presentation. I was wondering if you guys have given some thought to how this may be applicable to sort of science-related projects, perhaps like, I don't know, protein design or material science.
Yeah, that's interesting. So I'm not sure if we've thought about that specifically, but I mean, I know an area, so we have looked at sort of generative design for other, I guess, areas besides just, geometry generation. So we've had a couple projects using generative design for circuit design. So how would you design a circuit? And so generative designing alternatives and figuring out which, circuit is the easiest to build. And we also have done a few projects for generative design for architecture. So laying out, actually the office building we just moved into was designed using a generative design process where everyone put in their constraints about who they wanted to sit with and what kind of office they liked. And then the system generated thousands of candidate office layouts, which we then went through and built the best one. But yeah, that's a good idea. I mean, I think totally it could be useful for the domains you mentioned.
Thank you.
Okay, do we have any other questions for Justin?
Justin, can you hear me?
Yes.
So, I mean, so what kind of computing resources, go into this, optimizations or, of these designs in general?
Yeah, so that's, I mean, a bit outside of my particular expertise, but so in this particular project, it was all this topology optimization, which was, more or less minimizing the volume of a design while keeping the strength high. I mean, there's more to it than that. I'm sure the topology optimization guys in my group would, not want me characterizing it in that way. But at this time, it was all done on GPUs, and depending on the voxel size and other parameters, it would take between 1 minute and say 15 minutes of GPU time to generate one of these designs. We've since released generative design at Autodesk as a part of Fusion 360. And so all this is being done on the cloud, and I think actually it's moved away from GPU based solvers, but it still takes often upwards of 15 minutes to generate a single design, which is sort of a really big impediment to this becoming the sort of thing I'm imagining, where you would generate thousands of designs and then pick one, because you have to pay for these, this computing time. So it's, it's not really feasible to pay for 1,000 designs to just pick one, right? You're going to be more careful in your generation process. But I mean, I would really love there to be a way that, we could generate 1,000 designs, quickly and reasonably, and then allow for this sort of exploratory analysis, rather than just trying to get the design you've already got in your head.
Thanks.
Do we have any more questions for Justin? Yeah, I see. Tori?
Hi, yeah, this is Tori. Justin, thanks for your presentation. It's very interesting. I'm just curious, like, why would you want to create solutions or options that would fall over to start with? Like, don't you set the input parameters such that?
Sure. Yeah. If I had to go back again and set up this problem, I probably would have, added gravity and said I don't want them to fall over. So that, that's why I wanted to get rid of them in the first place. But so, speaking of how the solver was, it's considering that in that case that those ports, they're called, so the top and bottom are fixed. So if you imagine it being like glued to your desk and glued to the monitor, it would work. And so, when we talked to the designers, they were excited about this because they hadn't thought about making like a cantilevered monitor stand or like, incorporating that sort of thing into their design. And so, maybe they would make one that clamped to your desk and sort of,
and attaches to the ceiling.
Yeah, sure. But, at least sort of opening their minds to, areas they hadn't thought of, which, I think mostly when you think of a computer solving the problem for you, you're typically looking for this most optimal, super strong, super light way. But, if we can think of ways for the computer to generate, ideas or paths of exploration that, the human designers wouldn't have thought of by themselves, then that's, that's a different, I'd say more interesting, but a different way to look at how a computer could help in the design process.
Well, agreed, but it's only half the problem, right? If you don't, if there's no practical way to attach it to the ceiling or something, right? I mean, but the answer being that yes, you can put in whatever input parameters you decide are important. Is that true?
Yeah, no, I think in a more, normal use case, you might generate something, see that the things are falling over, say, ooh, that's not right. And then you'd add another constraint to the solver.
Well, hopefully you would figure that out first, but, but yes, yeah. Okay. Thank you.
Great, thank you. And do we have any more questions for Justin, or will we have a minute or two left for Alex? So Justin, let me thank you again for the great presentation. And I do have one question, and that regards pricing of the software. So as I mentioned when we emailed yesterday, that we are, this group, it's overwhelmingly academic users. And when it comes to things like software budget, it tends to be small. Is there academic pricing for this? Well,
yeah. So I mean, Autodesk itself has, all of our software is free for everybody with an academic email address. So at that level, all the software is available for free for everyone in an academic setting. For the generative design type thing where you'd have to use, what were called, cloud credits to do the generation, I think you'll get some to start off with, and then yeah, I think we're still sort of working out the actual pricing model. But I mean, if anyone's interested in doing sort of research in that area, you should contact me, and I suspect we could work something out. But at a basic level, yeah, all the software is free for.
Oh, okay, good. I didn't realize that. And as far as the computing, so we many of us are from either national or campus supercomputing centers. We do have the computing resources where we could do that generative design rather than going to the cloud.
Yeah, so I'm not sure if we have the ability, to actually. So I mean, you can do local solves or you can do cloud solves. I'm not sure, what the exact build out is for the capability for doing local solves. But I mean, that is very interesting because we do have clients, NASA or whatnot, that or people who have very sensitive designs that they wouldn't want to be done on a on a shared cloud service, right? They want to be able to do all their computations in-house, and so the ability to be able to run these things locally on their own clusters, is something that that a number of our customers are looking for. I'm not sure exactly what the what the state is of that.
Okay, I'd actually like to follow up with you on that at some point, probably after the holidays.
Sure.
And Alex, can I ask you one question from your talk?
Sure, go ahead.
Yeah, so you mentioned, I think it was your project with Brian Cougar, that some of the data, the exome sequence data, was acquired on the solid platform, that's no longer manufactured.
Yes.
Did that present any challenges? Like, is there, does open source software still support that format, or did you run into issues trying to process that solid data?
There's open source software that you can process solid data. I believe it's been a while since I've had the need to, but at least a few years ago, there still was open source software that was available to process the solid data. And really the model that Solid used is completely different than any other sequencing manufacturer. They represented bases in a 2-base encoded format, whereas most of the other sequencers just give you a single base. They don't have this 2-base encoding. So it was, I mean, it had some advantages, the technology, but it's, I for one, am not sad to see that it's no longer made.
Thank you. So we are now at 3 minutes past the hour. Again, thank you so much to our two speakers. These recordings and the slides will be made available on the ECSS Symposium site. For those of you who are ECSS staff, again, please think about presenting in the new year, and thank you very much.